Okay, get ready to look at biology in a way you have never seen it before. Not as some mystery that we study, but as a machine that we can engineer.
I mean, just think about that for a second. This is the core question. Forget everything you learned in biology class. We're not just observing life anymore. We are literally on the cusp of writing it. And that, well, that changes absolutely everything.
So, the first thing we got to do is make a huge mental shift. We need to stop thinking like biologists and start thinking like engineers. Because it turns out life isn't just a bunch of messy chemistry. It's an OS, an operating system. And look, I'm not speaking in metaphors here. We're talking about a real, physical rotary engine. This thing is smaller than a virus. It spins faster than a jet engine turbine, and get this, it runs with almost 100% efficiency. Nature built this thing.
And it doesn't stop with engines. Certain kinds of bacteria, like Geobacter, can literally grow their own electrical grid. These things are basically protein filaments that act just like copper wires. It lets bacteria export electrons. They can essentially breathe minerals. So yeah, we have biological wiring.
Okay, so we've got power, we've got wiring. What's the last piece of the puzzle? The factory, right? Well, meet the ribosomes. Think of them like nature's own 3D printers. They take digital code, the mRNA, and they print out physical stuff, proteins. So, there you have it. Engine, grid, factory. All the hardware is already there.
And this is the fundamental shift, the big paradigm change. You see, for decades, genomics was all about reading the code of life. But now, synthetic biology is about writing it. It's about programming these little natural machines to do completely new things.
So, what happens when you take this incredible biological hardware and you slam it together with another massive revolution? AI? And I'm not just talking about any AI, I mean agentic AI. Systems that can actually plan, act, and get things done all on their own.
This is a total game changer for medicine. Think about it. Right now, medicine is all reactive, right? You get sick, then you take a pill. But imagine a future where we have these engineered bacteria, like tiny little nanobots, just living inside us. A new virus pops up, we don't wait for a vaccine, we just push a software update to our internal bioagents, and boom, they evolve to fight it off, maybe in a matter of hours.
And this goes way beyond just medicine. You know how our silicon chips are kind of hitting a wall? They get too hot. Well, the next big leap could be what's called wetware, computing with biology. Imagine, instead of implanting some rigid chip into a brain, we grow a neural interface using those bacterial nanowires. It would be self-repairing, it would adapt, and the holy grail, the ultimate goal, it's an AI that works like a compiler for biology. You'd give it a simple command, like, hey, upgrade my memory, and it would spit out the exact DNA sequence to make that happen.
Now, I know this all sounds like some super clean, sterile science fiction, right? But the crazy part is, the reality of it is being built right now, in garages, and it's got this gritty, really functional vibe to it.
Yeah, this quote from the visual blueprints for all this research, it just nails the whole aesthetic. It's not about being sleek or polished. It's brutalist. It's all about making stuff that actually works, using whatever you can find, pure function over form.
And get this, there's actually a recipe for how to visualize this new reality. If you want an AI to generate images that look real, you have to ground it in stuff that's, well, kind of boring and mundane. You use an anchor object, like a Home Depot bucket. You add texture mismatch, like fuzzy mold growing on a fiberglass circuit board, and you use bad lighting. It totally strips away that perfect, sterile AI look and makes these impossible ideas feel like you could reach out and touch them.
Okay, so let's get down to the nitty-gritty. I'm going to walk you through a 4-step recipe for building a key piece of a biological computer, a synapse.
And the most incredible part about this whole thing is just how accessible it is. You're not using some $5,000 lab-grade anaerobic chamber. No, the rig is a Tupperware container with a couple of hand warmers thrown in to suck up the oxygen. You brew this living semiconductor ink using bacteria you can order online. You assemble the chip on a microscope slide with some copper tape, and you test it with a simple Arduino. I mean, this is literally revolutionary science being done with stuff you can buy at the hardware store.
So, the big question is, does it actually work? When you run the test, you're on the lookout for this one very specific shape on your graph. It's called a pinched hysteresis loop. And that funky-looking loop is the unmistakable electronic fingerprint of something called a memristor, which is basically a resistor that has memory.
And what does that loop really mean in plain English? It means this. That little biological component you cooked up in your garage, it remembered. It actually remembered. It changed its resistance based on the electricity that had passed through it before, and it held onto that change. You just built a biological synapse.
Okay, so we built one tiny component. That's cool. But now let's scale up. Let's integrate it into a whole system and build something, well, something truly radical. A wall that can actually see.
And we're starting right back in that gritty garage lab reality. Step 1 isn't carefully mixing chemicals in a clean little beaker. Nope. It's mixing up a batch of bioconcrete in a 5-gallon Home Depot bucket with a power drill. Just imagine this swirling mess of industrial primer, that black bacterial goo, and a white fungal culture.
Then, you apply it. You paint it on a wall. First, a conductive carbon base layer, then a middle layer of mycelium to act as the neural network, and finally a top coat of a light-sensitive biological paste. Think about that. You are literally painting a living computer onto a wall.
And this is the payoff. The wall itself, it just looks like a wall, maybe a weirdly painted one, but that's it. It looks completely inert. But when you stand in front of it, a laptop that's wired up to the wall suddenly displays a real-time heat map that perfectly matches the shape of your shadow. The wall is alive. It's sensing you're there, and it's reporting that data.
So here's the thing you have to take away from all this. This isn't science fiction anymore. The components exist. The protocols, the DIY blueprints, they're out there. People are building this stuff in their garages right now. Biology is technology now. The blueprints are on the table. The only question left is, what are we going to build with them?